All right, let's check the audio. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, it's good enough. Okay, so yeah, so the hidden variables, Einstein's solution that it's hidden variables. You can't tell me that it blew Einstein's mind, but he said it's just hidden variables. It's like, which is it? So Einstein apparently was smarter than everyone, and he gave the answer. This is the answer. It's a magic trick. The answer is hidden variables. Einstein could not have had his mind blown if he gave you the answer. It's one of the two. And the answer with the two balls, that's not the perfect answer because when when you test a particle, it always gives you a probabilistic answer. So it's unlike a ball a ball gives you on the macro scale, this looks red. If you look at the very, very tiniest red, you'll see there's some particulates of blue and a little bit of red in the blue. But when it comes to a tiny particle, like an elementary particle, then when we test it, it's probabilistic. The probability bubbles up. There is probability attached to the color of the ball, but it's insignificant because of the macro scale. But when it comes to the tiniest particles in the universe, then the probability bubbles up all the way up, and every measurement has a probability attached to it. That's the nature of the beast. So a macro ball is not a good example. And your claim that information can travel faster than light is obviously invalid. You yourself say so.
Learn a whole bunch of physics. But it's still perplexing. How is
You admit that it's perplexing. And you're asking the question and you don't seem to have the answer.
it that quantum mechanics can travel so fast? Well, there were some people, including Einstein, who thought that this wasn't so mysterious after all. Suppose
So which is it? You just said, listen to what you're saying. I mean, you have to get your story straight.
the outcome of the measurement of the first particle. That means that quantum information can travel faster than light. Yeah, you heard me right. Faster than light. That blew Einstein's
Okay, so you just said it blew Einstein's mind, but you also said
mind too. In fact, he co-authored a paper in Action at a Distance. Information move at speeds faster than light? Yeah, it seems to. But it doesn't invalidate when we compare the measurements, and that information can be transferred no faster than the speed of light. So that saves Einstein's theory, which is a relief. Otherwise, I'd have to learn a whole bunch of physics. But it's still perplexing. How is it that quantum mechanics can travel so fast? Well, there were some people, including Einstein, who thought that this wasn't so mysterious after all. Suppose
you got to make up your mind. See, when people don't have the story straight, that's where you have to start digging. Like the police, when they look for the murderer or the criminal, when they want to catch a criminal, they start interrogating. And all they look for is a contradiction. And once they have a contradiction, they know they know you're guilty, or they know you're guilty of a crime. Right? Something is wrong when you're contradicting yourself. All right, that's the end of that. So they know to start digging, and then they start digging. So when this guy, Dr. Don Corleone Lincoln, when he contradicts himself when he talks about Einstein, that Einstein was perplexed, was not perplexed. So which is it? Anyway, so what I think is that it did not blow Einstein's mind at all. Einstein figured it out right away. And the answer Einstein gave, I believe, is the correct answer. And the answer is hidden variables. So what I'd like to do is I'd like to write a simple Python script that reproduces this experiment. Right? If I can reproduce this experiment, then we're done. All we need to do is reproduce this experiment. We need to have particle 1 not communicate with particle 2, yet they need to flip a coin that seems to be entangled. So there should be one coin that's going to be the entangled coin, or the single wave function, right? So something has to be. They need to both know the answer. Now, Einstein said the answer is at the creation. So that's what we're going to try and do. We're going to create particle 1 and particle 2. We're going to give them equal but opposite spins in random directions. And we're also going to flip a coin that's going to be the coin of the actual measurement. The measurement coin is already going to be flipped at the creation, and the answer to the measurement, as far as the probability is concerned, is going to be shared. So the information which way to go is there's no reason to wait. The information, whatever is going to cause particle 1 to choose to go with the 1%, that's going to tell particle 2 to also go with the 1%. They need to share, so that, or the vice versa. If this guy flips the coin, this guy will also will not flip a coin. It's not that none of them will flip a coin. We're going to flip a coin at the creation and share the hidden variable of the coin flip. They're both going to have the flipped coin. They're not going to flip a coin in real time, because then they need to share the information, and there's no way they're sharing information. So we just need to flip the coin at the creation. Just like we're creating them with opposite but equal spin, we're also going to flip a coin at the same time of creation and share the answer of the flipping of the coin, so that when they need to choose, they don't need to flip a coin. They already have the answer to the flipped coin, and all they need to do is apply a deterministic function to the random number that was already pre-generated in order to know which way to go. And that should give us this magic trick, as if they're communicating faster than light. I don't see how this can fail. I can't imagine how this can fail. So, without further ado, let's begin. But you already, right? Whoever is listening, you can do this yourself. So we're going to go to ChatGPT and we're going to start explaining to ChatGPT what we would like to accomplish, right? We want to create a simulation We want to create a simulation. We want to create a simulation. This is the simulation. We want to create this. I'm not in my server. I am in my server. We want to create a simulation. We want to create this simulation. We want to create this simulation. It shouldn't be that difficult. We're going to be flipping each time. We're going to be creating two particles with equal but opposite spins, random spins. We don't know in what direction, except that they have equal but opposite spins. That's it. That's the first thing. Then we're going to generate a random number that represents the flipping of the coin of the decision of the detection. And we're going to share this number between them. Then we're going to ask each particle simultaneously. We're going to pretend that they're separated, and and not talking to each other, of course. And we're going to tell them both at the same time. I'm telling you, I'm testing you to the right, and I'm testing you to the left. Now let's assume, just like we did before, let's assume that this guy is at 901 and this guy is at 301. Right? That's the way they were created, at 901, pointing at 901 and pointing at 301. But this guy is being measured to the right, let's say. Now he doesn't flip a coin, but he calls the function that flips the coin and gives him the randomness. And the answer is some random number. But it's going to be the same random number that this guy will get because it's been predetermined. The randomness has been predetermined. And all that's left is to apply the randomness to the 1%. And this guy is also going to ask for the randomness with 1% because this guy is also, right, the 301 compared to the 9 p.m. That's going to give us 1%. So he's going to enter 1% into the random function. But these are right, it's a predetermined random function. The randomness, the random value has already been predetermined. So it's no longer a random function. It's not even pseudo random. It's just whatever answer this guy got, this guy will get. They're going to get the same answer. And that's it. And every time this guy will point to the right, this guy will point to the left. And this will also explain this experiment. This guy also, he's perplexed. How could this be? This is entanglement. This is schminkentanglement. Scientific American, give me more money. I want money. Yeah, should be very straightforward. I don't see how this can fail. I can't imagine this failing. But let's give it a shot. Zo, 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 zo. We go to Zo. We go to Mr. ChatGPT. Mr. ChatGPT, please write a Python script. Script. But I have to leave. Oh, what time is it? Yeah, I have to leave soon. So the Python scriptos. Okay. So create two particles. Each with a spin. Direction. Between 0 and 360. It can't be 0 and 360 because 0 is 360. So it's between 1 and 360 degrees. I can't imagine the next version of ChatGPT. You're just going to ask it, watch this video and refute it. Done. Okay. So write it, okay, between 1 and 360 degrees inclusive. So 1 and 360 are legit. Okay. Create two particles with opposite spins. each particle, each spin direction will be between 1 and 360 degrees inclusive. Generate a single random value. Share this random value between both particles. Okay, both particles now have this value. Measure or call particle 1, he called them particle A and B. Particle A, measure measurement angle, where measurement angle is the same. Where measurement angle is where measurement angle will be between 1 and 360 degrees inclusive. So measurement, okay, you're asking particle A, so call each, doesn't matter which. Call on both particles, particle measure, measurement angle, but you're going to measure, wait, which way are you going to measure? Are they both, yeah, we're going to measure opposite. So let's say call particle A, particle A, oh my God. Call particle A, measure measurement angle A, where measurement angle A, where measurement angle, where the measurement, where this measurement angle will be between 1 and 360 degrees inclusive. But which is it? So we're going to measure right and left. So let's say we're measuring angle is 0. But I want there to be an angle. Are they measured? Yeah, it's the same. It's the same protocol. We're measuring because we want one to be to the right and one to be to the left, so they have to be under the same influence. So it's the same measurement angle. But what is the measurement angle? There's no reason to change it. We just want to run the test again and again. So the measurement, we don't need a measurement angle. Measurement angle, where this measurement angle will be 0, whatever that means, will be 0 degrees. Whatever 0 means, I don't care. Some angle, it doesn't matter which. But the two particles are at some random, each spin direction will be between. So again, please write a Python script. Create two particles with random opposite spins. Each spin will be a number between 1 and 360 degrees inclusive. Generate a single random value and store this spin value with each particle. Generate a single random value share this value between both particles. Store this value, have both particles store this value. It wouldn't know, is it a shared value? It's what? Generate a single random value. Tell both particles this value. Create when in the creation. I have a better idea. Let's before we create. So when we create two particles with random opposite spins and the random value. Oh my god, there's traffic outside. I need to leave soon. Each spin will be a number between 1 and 360 degrees inclusive. Store this spin. I don't need to store the spin because I created them with the spin. Generate a single random value. Please write a Python script. Generate a single random value. Create two particles with random opposite spins and wait, but the spin itself could be used to generate a random value. We could use the spin. We don't need another. The spin itself is a random value. Create two particles with random opposite spins. We don't need a random value. We don't need it. Each spin will be a number between 1 and 360 degrees inclusive. Please write a Python script. Create two particles with random opposite spins. Each spin will be a number between 1 and 360 degrees inclusive. Call particle A measurement angle, where measurement angle will be is 0 degrees. So okay. I have to go 0 degrees. Now, when we measure, we want to randomly react. So measure, call both particle, call on both particles measure measurement angle. Well, measurement angle is 0 degrees. So you call on both of them. Now let's now measure should so what does measure do? Measure should return up or down depending on could it be could it be is it enough? Is the spin enough of a random? No, it can't be. It can't be enough. We need another. We have to have another random number. So generate a random value. Create two particles with random opposite spins and this random value. So you have this the random spin and the value. Each spin will be a number between 1 and 360. Call on both particles measure, where measurement angle is 0. Measure measure what should it do? Well, it should take the spin, and based on the spin it should decide, but then based on the random value it should decide on top of that what to do. So this the closeness should it should create a weight. It should create a weight based on the spin that gives the weight. And then it should generate, and then it should use the random value to decide which way to spin. If to do or not to do what it's told. But it should weigh based on the difference. The weight of the randomness so the weight of the randomness is not 50%. It flips a coin, but the coin is weighted. And it doesn't flip a coin. The coin has already been flipped. So the randomness is already, we have the randomness, but how much weight do we give to the randomness? The randomness is weighed by the difference between the angle. So measurement angle, it needs to decide which way, needs to decide up or down. That's what it needs to return. needs to return up or down. When does it return up? When does it return down? So it should consider measure needs to return up or down, but how do I explain this? It depends on how taking two things into consideration. Okay, to return up or down depending on the difference between its particles spin direction and the measurement angle. So it should depend on the difference between its particle spin direction and that, but it should then pretend to flip a coin, and the answer to the coin flip is the random value. So it should use that depending on the difference, and also depending on its particles random value. So it needs to also depend on the random value. But the random value should be weighted more lightly as the angle is smaller, or more heavily as the angle is bigger, up to 50%. I mean, the most is 50%. That's the most random. You cannot have more random than 50%, I guess. And also, depending on its particle's random value, the random value should be weighted more heavily as the or more lightly as the difference. So we need to define difference depending on the difference, as that we already defined. Okay, as the difference, as the above difference is smaller. So it's going to be as the angle difference becomes 0, the randomness becomes 0. What if the angle is 180 degrees? Then the randomness is also 0, with the randomness at difference 0 with randomness 0 at difference 0 and at difference 180 degrees. Run this test 1,000 times. Plot the results. The two particles must always be measured in opposite directions. Please confirm this prediction. Okay, let's see. I don't know, maybe it's too long. Maybe it's going to tell me, I don't know. Can it figure it out? And the next step, if of course, if this works, the next step is going to be to actually disprove Bell's theorem and the Nobel Prize. So we're going to send the Nobel Prize commission to go back to sleep. They actually gave a prize for entanglement or something? Okay. Let's see. Let's go to Google Colab. Let's create a new open new notebook or new something. What do you create? A new, I guess you create a new notebook? What is this? I don't know how to use this. File. Okay, new notebook, whatever. Waiting. Okay, so the name is going to be Quantum Entanglement is still utter nonsense. Okay, so we could generate the code with this guy as well. Let's see if this works. So I don't know if it understood everything I wanted to do. So this is wrong because this looks like it's 50-50. So it didn't get it. It did not understand what I wanted to do. Probability of opposite measurements in quantum spin experiment. The same and the opposite. They should always be opposite. This looks like 50-50. So this is wrong. So let's see. Okay. So in itself, spin angle, random value, spin angle, random value, that's fine. Measure. This is it. Let's take a drink of water. There's no reason in the world this should fail. There's no reason in the universe this should fail. I can't imagine this failing. This is the problem, you see? It's flipping the coin in real time. This is, of course, this is not allowed. It didn't use the random value that I told it to use. So measurement angle. Let me make a phone call. I'm in suspense. I'm in suspended animation. Hold on 1 second. One second, 1 second, 1 second. Give me a second. Okay, give me 1 more minute. Okay, 1 more minute. Okay, I need to go. Let's just finish this. So this is obviously incorrect. So measurement angle. This is so excitement. Okay, so measurement. Where are we? Where's the thing? Here's the thing. So measurement angle. So measurement angle is fine. So delta angle is the measurement angle minus the self spin. Okay, if it's bigger than 180, delta angle is 360, whatever. Probability weighting function based. Okay, so randomness. range from, oh, very good. This is the randomness weight. This is very nice. It's the sign of the radian of the delta. So 0 means zero randomness. Very good. And here is the random value. So the random value times the randomness, that's the probability up. So up if, don't flip a coin again, random up if probability up, else down. This should be 100%. No, this should always be opposite. So range spin A random, spin A. So spin B is spin A plus 180. Random is fine. Create two entangled particles with opposite spin directions. Particle spin A, spin B. Good. Result, particle A measurement angle, which is 0. Good. If result is not the same, then count cases where measurements are opposite. Okay. Calculate and plot the results. How could they be the same if their spin is opposite? They're both up? They're both up? How could you both be up? Particle A and particle B both say up for different spin angle? How? Yeah, I'm not sure about this. If delta angle is greater than 180, All right. The problem with this is I don't know exactly what it's doing. Why is how could it get the same? This is ridiculous. So let's just make sure that there's no problem. Okay, spin A is random one. No, 1 in 360. What do you mean 1 in 361? Between 1 and 360. Yeah. So it says here, generate a random spin direction between 1 and 360 and a random value between 0 and 1. Okay, so this is between 1 and 360. And then spin B is spin A plus 180. But if it's more than mod 360, random value is random value. Particle A is particle spin A, random value, and particle B, spin B. This looks good. Result A, measure. Result B, measure. That's good. Okay. And then you have result A and result B. What is result A and result B? Opposite counts. Where is it storing the data? Oh, it's not. It's just storing the count. So it's just counting. Now, opposite probability, opposite over number of experiments, that's fine. Everything is fine. Okay, so the problem can only be here. So delta is the measurement angle minus the spin. Measurement angle, that's good. Mod 360. Measurement angle, whatever angle it is, spin, and you never want more than 360. That's fine. Delta, if the delta between them is more than 180, then adjust for the smallest angle difference. I don't know if I like this. Let's remove this and rerun it. How do we know it runs and it's done and it's still the same? Okay, delta is an absolute value between the two angles down to 360. The randomness weight, so the probability up is 0.5. Wait, what? The delta, so the randomness, what is it doing? The randomness, right? How heavy is this guy? It needs to balance. It needs to balance between the random value and the delta angle. Anyway, I need to run up if probability is up. I don't know. I need to think about this. This is a little bit confusing. But it should work. I mean, there's no way in the world this is not going to work. Probability up is half. This doesn't make any sense. So we're always starting from half. So of course that's wrong. You don't start from half. So random value minus half. Why would you remove So it's a mix of the random value and the random, I would say it's just randomness weight plus the random value. The random value is between 0 and 1. And the randomness weight is between 0 and 1. So it's just one plus the other. The up is just the randomness is between 0 and 1, because that is what sine is. And the randomness is between 0 and 1. Wait a minute, what do you mean if probability up? Probability up is not an if. The question is, together, are they bigger than 1? It's up if probability up is greater than 1. Let's see. Okay, we're getting somewhere. Anyway, I'm okay, I gotta go. All right, you know where I'm heading, and the next step would be to use the same logic to disprove the Nobel Prize, and entanglement is done. It's a magic trick. It's just you go to see a magic show. This is like Penn and Teller. They watch a magician and they have to figure out how he did it. They have to reverse engineer the magic trick. That's all that this is about. It's really very straightforward. It's a joke. It's a complete and utter joke. Quantum entanglement is a complete and utter joke. Thank you so much for listening. All right, I gotta go. I'll be back and we'll figure it out. Bye bye.